Hello, everyone. In the continuation of our previous lecture, in which we have discussed the concept of a partially ordered set as well as a concept of partially ordered relation. We have also taken several examples to understand that what exactly a partially ordered relation is, how to check a given relation is partially ordered or not. Now, today we are going to discuss another important concept related to a partially ordered set known as a hash diagram. So, what is a hash diagram? Basically, the graphical representation of a poset is known as a hash diagram. Okay. So, first of all, the given structure should be a poset. If it is poset, we can draw it in terms of a diagram called as a hash diagram. Now, what happens? Sometimes it's difficult to give the input as a relation for some of the structure which is poset. So, in that situation, in place of giving the input as a poset or as the individual elements of a poset, it's easy to give the input in terms of a diagram that we called as a hash diagram. Okay, now let me share the screen to discuss it in more detail. So, as already communicated, a graphical representation of a poset is known as a hash diagram. When I'm saying graphical representation, means it is a graph. What is a graph? A collection of vertices and edges. So it is having some vertices, it is having some edges. Now, let us see that what are the steps which are involved to draw a hash diagram for a poset. The first one is what we are supposed to represent each points of the given set as a vertex or node, and connect it with the other vertices or nodes by an edge if they are related to each other. Means first thing, position the points of the set in the plane. If A and B is related, or I can say if A comma B belongs to R, then A and B will be connected by an edge. Then once we represent all the vertices and their between connection by edges, now there are three more steps. As we know that a poset is reflexive, a poset is a reflexive relation. So we will remove all the reflexive edges from the graph. That is, whatever the self loops are there are supposed to be removed from the graph. Then, same thing for the transitive edges. Since the poset is transitive, we'll remove all the transitive edges. How to identify what is the transitive edges? So if A comma B is in R, B comma C is in R, then the edge joining A to C is called as a transitive edge. That means from the hash diagram, we are supposed to remove this transitive edge. We should be very careful when removing the transitive edges. It's not that we can remove any edge. It must be the transitive one, which is how to identify. AB is there, BC is there, then A to C should not be there. Once we did all these things, whatever graph we obtained, we call it as a hash diagram. One important point over here is what? If we are supposed to follow a direction either from bottom to top or left to right. Most of the time we follow bottom to top. Some authors follow like top to bottom. What it means exactly? It means what? If A and B are related to each other, if A comma B belongs to R, so the input should always be on lower side to the output. This is what we mean by the direction, or we mean by the representation, initial vertex should always be on the lower side of the terminal vertex. The shape may be anything, like here is A, here is B. Yes, this is also allowed. Huh? Initial is lower than the terminal vertex. We should follow the direction always. Direction means it's not like A comma B is there. Let us see C comma D is also there in your R. So for AB, I am following the direction from lower to upper. And for CD, I am following the direction from upper to lower. This should not happen. Either we should move like this or this. It's not combinedly both the direction in a same diagram. Understood? So this is what the points that we are having to draw a hash diagram. Total three steps. First, called as a raw figure, where all the connections are represented. Second, remove the reflexive edges, that is all the self loops. The third one, remove the transitive edges, which is A comma C. It's not out of A, B, B, C, and AC we can remove any. No. A comma C should be removed. Finally, whatever we get called as a hash diagram, the shape of a hash diagram is not unique, but the connection is always unique. Two graphs or two diagrams may have the different shapes, but they should have the same connection. If they are having the same connection, we call those two diagrams as identical diagram. Let us try to understand it in more detailed manner by taking one example. So the question is what? Draw the hash diagram of the partially ordering A comma B belongs to R such that A divides B on this set. So what it is given, that means A comma B belongs to R if A divides B. And from where these A comma B comes, it comes from the given set. We can write this set as set A. Okay, so the operation is given as operation of divisibility. Let us try to write it. So first raw step, indicate all the elements as the vertices. So let us see, this is 1, somewhere 2, somewhere 3. When you are positioning the vertices, the element as vertices, do remember the hierarchy. Okay, 1, 2, 3. Then somewhere here, let us take 4. Somewhere here, let us say 6. Then 8. Then somewhere 12. I just put them so that the smaller is on lower side, the larger is on upper side. If they are not numbers, we can put randomly anywhere, just taking care about the relation. If A is related to B, then A should be on lower side than B. Understood? Now, what it is given, the operation is divisibility. So as we know that the operation is divisibility means A comma B belongs to R if A divides B. So 1 divides 2, yes, connect 1 to 2. 1 divides 3, yes. 1 divides 6, yes. 1 divides 4, yes. 1 divides 8, yes. Then 1 divides 12, yes. 1 divide itself also. So these are all the connections that one is having. Since 1 divide 1, 1 divide 2, so operation is divisibility. I represent everything, every pair connected by edge, if they are related to each other. Talking about 2. 2 divides 3? No. So 2 and 3 will not be connected. 2 divides 4? Yes. So 2 to 4 connected. 2 divides 6? Yes. So 2 to 6 connected. Do remember, the shape does not matter. Okay, it may be any shape. 2 divides 8? Yes. 2 divides 12? Yes. 2 divides itself? Yes. Now all the connection of 2 is completed. Talking about 3. 3 divides 2? No. 3 divides 6? Yes. 3 divides 4? No. 3 divides 8? No. 3 divides 12? Yes. 3 divides itself? Yes. So all the connection for 3 done. Talking about 4. 4 divides 8? Yes. 4 divides 6? No. 4 divide 12, yes. 4 divide itself, yes. All the connection of 4 is done. Talking for 8. 8 divide 12, no. 8 divide 6, no. 8 divide 8, yes. So all the connection of 8 done. Talking about 6. 6 divide 12, yes. 6 divide itself, yes. So this is what the raw figure. The raw figure where I represented all the edges, all the relation. Does not matter it is reflexive or transitive. If they are in R, I draw that. Another way is what? Write all the elements in R, then draw the connection in it. Or we can draw it directly, no problem. Now, step number two. In step number two, what I supposed to do? I supposed to remove all the reflexive edges from it. I supposed to remove all the reflexive edges from it. Reflexive means what? All the self loop are supposed to remove. So let me remove it. I am doing altering in the same diagram. So 1 1 should not be there. 2 2 should not be there. 3 3 should not be there. 4 4 should not be there. 6 6 should not be there. 8 8 not be there. 12 12 should there, but when I remove it, it will remove. So this is the step number two. All the reflexive edges are removed. Now the step number three, we are supposed to remove all the transitive edges also. Whatever the transitive edges are there, it should not be there in your diagram. It should not be there in your diagram. Now transitive means what? Let us try to understand it first. Transitive means what? If A comma B belongs to R, B comma C belongs to R, then A comma C belongs to R. So transitive means what? If AB is in your R, BC is in your R, then this A comma C is in your R. This is called as a transitive edge. This is called as a transitive edge. So we are supposed to remove this edge from the diagram. So let us see the transitive edges. Just see 1 comma 2 is there. This is your 2. 2 comma 4 is there. 1 comma 4 is also there. Let us write it. 1 2 is in R. Yes. 2 4 is in R. So what will be transitive? 1 4. So 1 4 is a transitive edge. It must be removed from the graph. So let us remove this 1 4 from the graph. Let us remove this 1 4 from the graph. So 1 4 is removed. Oh, 2 4 is also removed. Let me draw it. It should be there. So I removed what? 1 4. I remove 1 4, which is the transitive one. Now you can see this is also transitive because 2 to 4, 4 to 8, 2 to 8. So 2 8 should also remove from this graph. Remove 2 8 also. Now let us see other transitive edges also. 1 4, 4 8. 1 8 should not be there. 1 4, 4 12, 1 4 should not be there. 1 3, 3 6, 1 6. 1 6 is transitive then. Now see 1 2, 1 2, then this is what 2 1 2, then 2 2 6 is also there. 1 2 6 is not there, which is not there, done. Now 3 6, 6 12, 3 12 should not be there. Transitive. Okay, so in the same manner, is there any other transitive edge? Let us try to check it. So is there any other transitive? Yes, this 2 to 12 is also transitive edge. So let us remove it. How it is transitive? 2 to 6, 6 to 12, 2 to 12. 2 6. It is from outside. That's why looking in a different manner. 2 to 6 is there. 6 to 12. 2 to 12. Remove it. So I think, is there any other as is needed? No. So this is what finally we obtained a graph which do not have any reflexive and transitive edges and representing the given relation. This is what you can see it in a neat and clean manner. The first one is the raw figure. The second one, where we remove the reflexive one. The third one, where we remove the transitive one. Now, some author used the direction, some did not. Okay, so it's your choice whether you want to use the direction or not. So this is how we draw the hash diagram of the given problem of the given partially ordered set. This is the final diagram. The thing is that uh, if you can draw it directly. Just keep in your mind that no reflexive edge should be there, no transitive edge should be there. Taking one more example. Now this time they are asking draw the hash diagram for the relation of subset on the power set of S where S is this thing. So what is your poset? Power set of S with the operation subset. That means I can say A comma B belongs to R if A is a subset of B. This is how the relation R is defined. From where this A comma B comes? They comes from power set of S. So the thing is that first we should know what is power set of S. The power set of a set is collection of all the subsets of a set. So here the set is ABC. What are the possible subsets of this set? Let us try to write it. Firstly, all the singleton. A is a subset of ABC, B is a subset of ABC, C is the subset of ABC. These are the singleton. Then pairs. A comma B is the subset of ABC. A comma C is the subset of ABC. B comma C is the subset of ABC. And A comma C is the subset of ABC. So these are the pair which is subset. Talking about triplets, so only one triplet, and phi is the subset of every set. Let us count them 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why 9? Okay. This AC repeatedly. I write twice this AC. Okay. So since we are talking about sets, so repetition of elements is not allowed. So this is what power set of A we are having. Okay. Now let us try to draw the hash diagram. As in the last example, they are numbers. So it's easy to place them. The larger on the upper side is smaller on the lower side. But here they are, we didn't know A is larger, B is larger, or C is larger. Larger is decided on the basis of the relation, which is subset over here. So I'm just putting it uh, 5, then all the singleton elements, singleton A, then singleton B, then singleton C, then pairs, then pair A comma B, then A comma C, then B comma C, and finally the largest which is A, B, C. Two elements which is not related to each other, can we put it on the same label? Okay, like this A and this B, I put it on the same label. They can be put it because they are not related to each other. Can I say this is the subset of this? No. So they can put it on the same label because they are not related. I'm trying to draw it directly without drawing reflexive and transitive edges. Now connect it layer wise. Phi is the subset of every set. So I will connect it with the first layer only. Because when I connect phi with AB like this, so A is subset of AB also. In this case, this will become transitive edge. Like 5 is a subset of A is the subset of AB, 5 is a subset of AB. In this case, phi to AB will become the transitive edge. So I am not drawing it. So what I'm exactly doing, I'm connecting them layer wise. A is a subset of AB, yes. A is a subset of A comma C, yes. A is a subset of B comma C, no. I will not connect it with the upper layer ABC because when I connect AB to ABC, this A to ABC will become transitive. Now B, so B is a subset of AB, B is a subset of BC, C is a subset of BC, C is a subset of AC, AC is the subset of ABC, BC is the subset of ABC. Now, this is the Hasse diagram of the given poset. It do not have any reflexive edges. It do not have any transitive edges. Okay, so this is how we can draw the Hasse diagram of a given partially ordered set. There are three steps. Step number one, locate all the vertices and connect a vertex A to B by an edge if they are in R, if they are related. Step two, remove all the reflexive edges. Step three, remove all the transitive edges. Whatever left over is your Hasse diagram. The shape of a Hasse diagram does not matter, but we should be very careful. If A is related to B, then A should be on lower side of B. Okay, so this is all about the Hasse diagram. So, okay, this is all about the Hasse diagram. I hope you understand it. Now, let us close this session. In the next class, we will continue this lecture series I'm planning in the next class to talk about some important terminology of a Hasse diagram. Then we'll cover the concept of lattice also. Now, going to close this session.